Ever pondered how our brain makes sense of the world around us? Picture this: a vast interconnected web of neurons, each firing and communicating, forming a complex network that drives our every thought, action, and perception. This intricate system is the inspiration behind a concept that's revolutionizing the way we interact with technology: neural networks. Neural networks are a type of computational model inspired by the human brain. Just as our brain is made up of billions of neurons working in harmony, neural networks consist of layers upon layers of artificial neurons, or nodes. These nodes, much like their biological counterparts, receive inputs, process information, and generate outputs. The structure of a neural network is quite fascinating. It's composed of multiple layers, each serving a unique purpose. The first layer is the input layer, which receives the initial data to be processed. This data then travels through one or more hidden layers, where the magic of learning and adaptation occurs. Finally, the processed information reaches the output layer, delivering the result of the computation. And how do these layers communicate? Through connections, of course. Each node in a layer is linked to every other node in the next layer through a connection. These connections aren't just passive conduits, they're weighted, meaning the influence of one node on another is determined by the strength of their connection. But what's the purpose of all this complexity? Well, neural networks are designed to learn. They learn by adjusting the weights of their connections based on the information they process, much like how our own neurons strengthen or weaken their synapses based on our experiences. In essence, neural networks are the backbone of artificial intelligence, making machines learn like humans. They're the key to making our devices smarter, more intuitive, and more capable than ever before. So next time you ask your smartphone a question, remember, you're witnessing the power of neural networks in action. So, what builds up these neural networks? It's the neurons. Now let's delve a little deeper into the world of neurons, the basic building blocks of neural networks. Picture a bustling city at night, with lights flickering on and off, sending signals to each other. That's what a neural network looks like, with neurons as the city lights. Neurons, in essence, are computational units that take in inputs, process them, and produce outputs. Each neuron is connected to many others, forming a vast, intricate web. These connections aren't just simple links, though. They're channels for information, allowing data to flow from one neuron to another, much like whispers passing through a crowd. But how do these whispers, these bits of information, travel? Well, they're carried along by something called weights. Weights determine the importance or influence of an input. Picture it like this. If a neuron is a city light, the weight is the intensity of that light. The stronger the weight, the brighter the light shines, and the more influential it is in the network. But there's another player in this game, the bias. If weights are the intensity of the light, biases are like the dimmer switch. They adjust the baseline intensity of the neuron's output, tweaking it just enough to keep things in balance. Now imagine thousands, even millions of these neurons, each with their own weights and biases, all interconnected, passing information back and forth. It's mind-boggling, isn't it? Yet, this is how your neural network operates, with each neuron playing its part in the grand scheme of things, working together to solve complex problems. So, just as a city is made up of individual buildings, each with its own purpose and function, a neural network is made up of neurons, each processing information in its unique way. And just like how cities grow and evolve over time, so too do neural networks learn and adapt, constantly changing and improving. Thus, neurons are the fundamental units of a neural network, much like cells in our bodies. Now, let's untangle the layers of a neural network. Imagine a neural network as a bustling city. The information, or data, is like a traveler embarking on a journey through this city. The city is divided into three distinct areas: the input layer, the hidden layers, and the output layer. The input layer is the city's grand entrance, the gateway. It's here that our traveler, the data, first arrives. It represents the initial raw data that we feed into our neural network. This could be anything from the pixels of an image, the words in a text, or the notes in a melody. From the input layer, our traveler sets off on its journey, moving into the hidden layers. These are the heart of the city, filled with countless pathways and connections. The hidden layers are where the magic really happens in a neural network. Here, The raw data from the input layer is processed, transformed, and analyzed. The hidden layers are composed of numerous nodes, or neurons, each performing specific calculations on the data. As our traveler moves through these layers, it's continually changing and evolving, much like a tourist soaking in the sights and sounds of a vibrant city. Finally, our traveler reaches the output layer, the city's grand exit. This is the final destination, where the processed data from the hidden layers is compiled and presented in a form that we can understand. If our neural network was designed to recognize images, for instance, the output layer might tell us whether the input data represented a cat, a dog, or a car. These three layers, input, hidden, and output, are all interconnected, allowing data to flow freely from one to the next. Each layer has a specific role to play, and it's the combination of these layers that allows a neural network to analyze and interpret data in incredibly complex ways. These layers work together, transforming raw data into meaningful output. Ever wondered how a neural network learns? Well, it's a fascinating process that involves two major components: training and activation functions. In this scene, we're going to dive into these concepts. Let's start with training. It's like teaching a puppy to sit or fetch. You show the neural network an input, like a picture of a cat, and tell it what the output should be. Say, "This is a cat." If the neural network gets it wrong, we adjust the weights and biases of the neurons in the network. This is done so that next time, the network is more likely to get it right. This process is repeated with tons and tons of data until the neural network can accurately identify cats, dogs, and maybe even distinguish between a Maine Coon and a Siamese. Now, how do we adjust the weights and biases? This is where backpropagation and gradient descent come into play. Backpropagation is like a feedback mechanism. It calculates how much each neuron in the network contributed to the error. Gradient descent, on the other hand, is like a hiker trying to find the quickest route down a mountain. It adjusts the weights and biases in the direction that minimizes the error. Over time, this process helps the network find the optimal weights and biases that yield the most accurate predictions. The second major component is the activation function. It's like the decision maker in the neuron. It takes the weighted sum of the inputs, adds the bias, and decides whether the neuron should be activated or not. There are several types of activation functions, such as the sigmoid, tan, and ReLU. Each has its own advantages and disadvantages, and choosing the right one can significantly affect the performance of the neural network. So there you have it. Training a neural network is a complex process involving error calculation, optimization techniques, and decision-making. But the end result is a powerful tool capable of learning patterns in data and making accurate predictions. Just like a child learning to walk, neural networks learn from their mistakes and improve over time. So, what can we achieve with these neural networks, and what are their boundaries? Let's dive in. Neural networks, like the human mind they're modeled after, are capable of a broad spectrum of tasks. One of the most common applications is image recognition. Through a process known as deep learning, neural networks can identify patterns and objects within an image, making them invaluable in everything from medical diagnostics to autonomous vehicles. But they don't stop at images. Neural networks also excel at language processing tasks. They can translate languages with remarkable accuracy, understand the context of sentences, and even generate human-like text. This is the technology behind your phone's voice assistant and the automatic captions on your favorite streaming platform. However, as impressive as these feats are, neural networks are not without their limitations. They are notoriously data-hungry, requiring large amounts of information to learn effectively. This can be a hurdle in situations where data is scarce or difficult to gather. Moreover, neural networks are prone to a problem called overfitting. This happens when a network learns its training data too well, to the point where it struggles to generalize its knowledge to new, unseen data. It's like studying for a test by memorizing the answers to past questions, only to falter when presented with a slightly different question on the actual exam. Another challenge is interpretability. Neural networks are often referred to as black boxes because it's difficult to understand how they make their decisions. This lack of transparency can be a serious issue, especially in fields like healthcare or law, where understanding the reasoning behind a decision is crucial. Neural networks, though powerful, are not a panacea. They have their limitations, but they're ushering in a new era of technological advancements. As we continue to refine and develop these networks, we can look forward to even more exciting breakthroughs in the world of artificial intelligence.